Okay, yeah, thank you, Lenka. And thank you, Florent, for having me. And this is better. For having me and for organizing the school, even under these adversarial circumstances. And so what I'm going to talk about in these two lectures today and on Friday is some recent stuff that we've been working on, but also that I feel the community as a whole, the people who are interested in neural networks and in their theory are getting interested in. So I hope it's going to be useful for you. And the question is basically, what's the impact of data, and in particular of the structure in data, on learning with neural networks? Okay? So obviously the data that we're using neural networks that we train them on, like images, natural language, games of Go, all these things, they're very structured in the sense there's a lot of redundancy in the data, there's non-trivial correlations. If you think about an image, there's some spatial structure in 2D there, natural language, there's some temporal structure. And obviously neural networks are really good at picking up this structure, from large data sets and then using that to generalize well to new tasks, okay? But from a theoretical point of view, how this works, so how neural networks extract and find the structure and how they store it and how they use it, it's very poorly understood, okay? And people have realized that this is one of the gaps between what we can do in theory at the moment and what's going on in practice. But we probably want to close if we want to get a bit of a better understanding in terms of what makes neural networks do as well as they do, okay? And so, what we're going to look at in these lectures are sort of several approaches to look at simple data structure in models of two-layer neural networks, okay? And so I'm going to start on the blackboard and then later I'm going to have some slides. And please, feel free to ask questions at all times. That worked really well in the other classes, so let's keep that up. To be concrete, let's fix the setup for most of what I'm going to be talking about, okay? And let's say that we're going to be interested in supervised regression tasks, okay? Supervised regression tasks in which you have high-dimensional inputs x, which live in R to the n. And so I'm, giving away that I'm a physicist by training, by choosing the n here. And you have a label or a response that's a scalar, okay? And so, there's a data distribution qxi. And you don't have access to this distribution, of course, but you're given maybe a big data set, or maybe you're given the opportunity to sample from this distribution continuously. And what you want to do is you want to learn a function phi that's parameterized by some parameters theta that will perform the prediction. Okay? And in particular, since we're talking about neural networks, we're going to specify the function class as two-layer neural networks that can be written, this should be a k, up, like this. Okay, so you have first layer weights w, you have second layer weights v, you have a nonlinear function g, that could be a ReLU, that could be a sigmoid, whatever you want. And we're going to look at this model in the limit where the input dimension is very large, okay? So that's the thermodynamic dimension. And the number of hidden nodes in your network is of order 1. And you have a scalar output, okay? So k is going to be order 1. Okay. Yeah, yeah, up. Okay? And there are two key quantities that we're going to be interested in. And in particular, these are the training error. So here I've given you p samples, and now I'm asking you, okay, what's your current prediction error on these p samples that you're actually training on? So that's going to be and since we're looking at regression tasks, we're going to be focusing on the quadratic error, okay? But then, of course, the quantity that we're really interested in and that we really want to understand is, of course, the generalization error, which is the expectation of this quadratic error, but now taking over the whole distribution Q, okay? Now, this is, of course, something that's not usually accessible, but we're going to look at cases where we can compute this, or at least say something about the behavior of this guy. Okay? That's the setup. So basically what I'm asking is, what's the impact of this guy? What's the rho? How does it affect generalization? And now there's sort of, if you will, two general approaches with which you can deal with this data distribution, okay? The one is you can say, well, actually, I don't care so much about the data. I really want to understand something about, the algorithm that I use to train this model, for example. So I'm going to try to prove things with as little assumptions on Q as possible. I'm just going to say Q has some bounded support on some space and whatever, and then try to prove something about that, okay? That's a road that's usually taken in statistics and in theoretical computer science, okay? And it has the advantage of being very robust to sort of any data distribution. But it, of course, has also the disadvantage that by saying any data distribution, you're also including any sort of adversarial data distribution that could mess you up and that might be very unrepresentative of what you really find in your data set, okay? Now, there's a complementary line, if you will, and that's saying, well, actually, let's put in a concrete model for QXY, okay? Let's put in some structure here. Let's give up some of that generality, and let's see how the structure that I put into this Q shows up in the learning dynamics, right? Now, the classic example of such a data model is, of course, our beloved teacher-student setup. That goes back to, the early days of statistical physics and neural networks, and the seminal works in particular of Elizabeth Gardner and Derrida. So this is sort of one classic reference, the model B, if you will. And the idea is very simple. So for the inputs, we're going to say, well, we're going to take them, so this is a high-dimensional vector, right? So we're going to take it element-wise IID from the standard normal distribution. Okay, so this is a normal distribution with mean 0, unit variance, and I draw my input vectors element-wise IID from this distribution. And then I generate a random neural network, a teacher network, and I will say that my labels Y are the output of this teacher network, okay? And for this teacher network, we can choose the same sort of two-layer network that we did for the student. I'm going to denote its weights always with a tilde, okay? And up. Okay, and now I can ask, okay, how does the structure of the teacher, how does the structure of the data show up in the generalization error? For example, if I have, k equal to 3 hidden units in my student, I have a teacher with just 1 hidden unit, how does this overparameterization help me? Or vice versa, what if my student is much smaller than the teacher, what's the approximation error, that sort of stuff. There are lots of studies on this model, as you very well know. We've been talking about it a lot here. And it's also picking up some interest beyond statistical physics, like more and more works also in theoretical computer science. In statistics, they're starting to have this planted model or this teacher-student setup and then analyze it with their methods, okay? But there's also, some disadvantages in this model, right? So earlier I was talking about understanding how structure affects learning and what the impact of structures in the data. Now here there's structure in the task, if you will, okay, in the function of your inputs that you're trying to learn. But the inputs themselves, they're very unstructured. They're about as unstructured as it gets, right? This is sort of a maximum entropy distribution for your inputs. So one of the things that we wanted to do was kind of, find a new teacher-student model where these guys have some more structure. And I'm going to show you one way to set up such a model now. And then the question becomes, okay, what can we still say analytically about it, right? Because the nice thing about this model is that there's plenty of things that we can do analytically or numerically. What can we say about a case where X is more structured? Okay? So let's make a little bit of space. Like this. So the model that I'm going to discuss in these lectures, we're going to call that the hidden manifold model, or if you will, the deep hidden manifold model. And I hope that the name will become clear in a few minutes. So again, what this model is modeling is the data distribution, okay? And the way we're going to get some data out of this model is as follows. we're going to start with a latent vector that we're going to call C. Okay, and that lives in D dimension, and this vector will be element-wise IID from the standard Gaussian. Okay, and then we're going to feed this random vector into a generative neural network. Okay, so one example of such a network would, for example, be a GAN, right? So these are the models that Max, or these are some of the models that Max Wadding was talking about. And the way they work is you basically have your data set with images, for example, just images. And you're training this neural network to model the distribution of the images, right? To get an approximation of this image distribution. And the idea is then that if you feed some random noise into this model, and you propagate that random noise through the trained network, what comes out at the end looks a lot like, you know, the images of cats and dogs that you trained the model on in the beginning, right? So this is a generative model. And really, you could put in pretty much any model that Max discussed last week here. And that will give you your input X. Okay, and this could, for example, be, you know, a face. That's how you get your X's. Now we still need a label, okay? And so in the classic teacher-student setup, the idea was, okay, well, you just choose a function of your inputs X, and that's going to give you a label, and then you're sort of trying to find that function, right? Now, if you think about the class of an image like this, right, it shouldn't really depend too much on every single pixel in the image, right? There should be some sort of higher level features that really determine whether this is an image of a cat or a dog, and which value, you know, the value of each pixel that is encoded in X shouldn't matter too much, right? And so what we're going to do here is we're going to implement this idea by saying that the teacher network, is acting on the latent variable C rather than the inputs X, okay? So here we're going to have a two-layer network of the kind that I just wrote down here, okay? And this gives me my Y. Now, a good example for this is, our generative adversarial networks, which are conditional, right? So some of these networks, you actually tell them you train them on an image set with 10 classes, and then as part of this vector C, you actually tell the network which class of image you want to generate, right? So I want to generate the image of a dog, and here's a Gaussian vector to start with. And so this is the idea that this teacher then should act on these latent variables C to capture that.
The number of examples of C is the same as the number of inputs you generate from the GAN?
Yes, if you will, there's a mapping, and for every input X, there's going to be a variable C, and we're going to call that the latent representation. Okay?
I mean, in principle, you can generate many more samples from this distribution, right? Then you put it.
Then, I mean, for every input that you generate, you will have to start with some latent variable here. Okay? So that's sort of the model. That's the hidden manifold model. Now, what's the hidden manifold in this model? Okay. Now, you can think about this in terms of this generator. Another way to think about it is more geometrically, if you will. And the intuition here is that if you think about images in, you know, like Cypher or MNIST data sets, which live in these really high-dimensional spaces, like 3,000 something for Cypher, they're really only living in a really small subspace of this space. Okay. In fact, there's different ways you can measure this, but for example, with kernel methods, maybe Mathieu will talk about this. But what happens if you do this? You see that your images actually are concentrating on a low-dimensional manifold in your high-dimensional input space. Okay. So if I sort of illustrate my high-dimensional input space with this 3D space, images are not dense, right? Most of the random points in this image. In this space, they will just be random garbage. But if I want to have really an image that shows something, that shows a dog, all these images will be sort of concentrated on this low-dimensional manifold. Okay, and of course, it's really hard to sort of write down this manifold or to even define it well. But you can really measure it, right? And so, for example, Mario and Mathieu and their group, they measured these manifolds using kernel methods, and then you'll find that, for example, for MNIST, this dimension is 15. Or for Cypher, it's sort of 35. So it's really much lower dimensional than the input space of the image. And so one way to think about this is that by drawing a latent vector C, you're really just choosing a point here on this low dimensional space, right? So you have D smaller than N. And you can think about this whole business of the generative network as just a really complicated function which then projects you from this lower dimensional manifold to somewhere in this high dimensional input space. But your inputs still keep this sort of low dimensional structure. And that's what's the hidden manifold part of this model. Okay?
What's the difference between the two theories? So, I mean, is there a way to map the dimension of the intrinsic dimension of data that people like lie and insist on looking at? Where they just look at the data and they see how much points lie on in the big space, and you can characterize just the intrinsic dimension without any notion of machine.
Yeah. This is very related. So what you're referring to is this paper from Laius group from last year. So what they basically did is they didn't just mention the intrinsic dimension of sort of your data, of the input that you feed in, but they also measured the intrinsic dimension of all the representations of the network as the input propagates through the network. Okay, and they showed how that changes over, as you go along the network. And so this is, if you will, sort of the time zero step of this process.
What's the reference for this?
This is a paper from Alessandro Laius group. This was NeurIPS last year, I think, measuring the intrinsic dimension of. I'll send it around. It's a really nice paper.
So what you're saying is that you can view your generative model as a map from the hidden manifold in the big space.
Exactly.
I mean, as an embedding of your manifold.
Exactly. It's a really complicated sort of function, right?
Yes.
But yeah, that's exactly the one. That's sort of the geometric way to think about it.
That's how you define the hidden manifold.
Yeah.
Full-time.
Yeah, exactly. Okay. So now basically the question becomes, okay, this is very nice to write down, and there's this nice sort of geometric analogy, but what can we say about this model analytically? Can we say anything? Okay. So that's going to be sort of the question for these two lectures. And we're going to start with a slightly simpler generative model with a just single layer thing. And first of all, see how that connects with the random matrix theory that Alice introduced last week. Okay. But I promise we'll get back to the GANs at some point. Okay, let's start with a first approach to this problem. Okay, let's say we do linear regression. So this is basically the case where you have one hidden unit in your student network, and the activation function G is just linear. Okay, and we're going to start with a one-layer random generator. So in other words, my inputs, my inputs xn is going to be a function that can be written like this. Okay, so this is sort of the activation function of my generator. And these guys are the weights of my generator. And for the moment, I'm going to say that they're random. Okay? And so, you can collect basically these weights in a matrix R to the n times d, right? And so this is now my generative model for my data, right? I still have the teacher acting on the C's, which is a two-layer network. And here, because it's a linear regression task, I'm going to take a linear teacher too, okay? With some nice normalization. And my student is also going to be linear. Now, we've seen this problem before, last week in Alice's lecture. Okay, we were just using very different words to describe it, and in fact, we were using a very different sort of semantics to describe it. Okay, so another way to think about this is to say, well, actually, my C are my inputs. Okay, that's the label of my inputs. And now, to solve this problem, I'm going to do random features, right? So I'm first going to blow up my inputs into a higher dimension. I'm going to apply nonlinearity, and then I'm just going to do a linear regression on the output of this regression layer, right? This is also related to these kernel methods, and the reference here is usually the famous Rahimi-Recht paper that Florent also talked about. And so the difference in semantics, if you will, is that here, this part of the model is the generative model of your data, right? And you only get to play with this. Whereas in the random feature, this is part of your analysis pipeline, right? So this is sort of the big semantic difference. But mathematically, they're absolutely the same model. And so because your matrix A is random, we can actually use random matrix theory to analyze it, okay? And this was done by Loire, by Liao, and by Couillet in 18, and then May and Montanari also wrote a really nice paper on this in 19, okay? And so sort of the two technical challenges that we have to deal with now are the non-trivial correlations in your X for your regression problem, and that your student and your teacher are not acting on the same space, right? One is acting on the C's, the other one is acting on the X's. Now let me just quickly remind you sort of what these results look like from our point of view now, from this new semantics, okay? So as an algorithm, we're just going to do a ridge regression. Okay, so we're going to say our weights are argmin of of your data set. And we're going to have some ridge regression term here. Okay. And what's nice about this problem is that you can then write down the solution explicitly, right? This is just given by this formula. This is the identity. Up. And so if you focus, for example, on the training error for the moment, okay, you can see, and again, this is taken from Alice lecture notes, which are excellent, and online. You can write this as the derivative. Of this quantity. And this term in random matrix theory is called the resolvent of the random matrix, okay, of XTX. Now, it turns out so basically that in this setup, you can write the training error for pretty much any x as a function over the spectral density of this covariance matrix XTX, okay? Now, in general, this covariance matrix will be intractable, and what Alice basically showed us is that Loire and May, they found a way to replace the spectral density, which is intractable, with a spectral density of another matrix, which is tractable and which has the same statistical properties, okay? So in other words, you have this theorem that theorem, and this is an informal statement where we say, okay, let phi be the expectation this is just the expectation of XX transpose, right? And then we can say that and delta gamma is obtained from some fixed point equation, okay, that I'm not going to write down explicitly. Okay, so this is the first instance of dealing with structured data. So what they say is, well, okay, we replace all these integrals that appear in the training error over this spectral density with integrals over the spectral density of another matrix that we can control. And then we can perform this integral to calculate the training error, and we're done, and we're good. Okay? So in other words, they have found a replacement of the real data matrix with a slightly different matrix that for the purposes of this linear regression is statistically equivalent. Okay? Now that's very nice. And in fact, there's already certain aspects in the solution that will show up later. There's a certain universality here, right? So I haven't really specified this activation function, if you will. And all that matters of this activation function is the expectation in this sort of kernel matrix, as it's called. Okay? So there's a certain universality here, and we're going to find this back in later results too. That's very nice. What's important, and what I want to stress here, and this is why I'm sort of repeating it here, are the two ingredients that you need for the solution, for this path. Okay? The first is we really made use of the fact that we can write down the solution to this linear regression problem explicitly. Okay, it's just a random matrix. It's random because of the data, and then we can analyze it. The second part is that in this linear regression problem, the training error is actually a function that can be written as a function of the spectral density of the covariance matrix. Okay, and so because the weights of my generator are random, I can use random matrix theory to deal with these integrals. Right? So that was really nice progress. But of course, we were talking about this in terms of generative models, not random features. For random features, having a random matrix here is perfectly fine. It's actually exactly what you want. But if you want to train the generator, you will want to have some non-trivial correlations in your matrix A. Okay? And that is something that random matrix theory cannot handle yet. Okay? So what we're going to try to do now is say something about this setup, this single layer generator, but now we're not going to assume anymore that these guys are IID random. Okay? It would have been a better effect if I had written down the IID random in the beginning. Okay. Are there any questions on this?
What
Yeah.
is
P is the number of samples, of training samples that I give you. Here I've only written this for the training error. And if you do the calculation, you actually see, that's maybe another comment, that you need to assume basically nothing on the data matrix. You only need to know basically this expectation. Okay? If you then want to say something about generalization, you need a little bit more work because you sort of need to connect the properties of the whole distribution to the properties of your subsample that you use for training. But this can still be done, it's just a bit more involved technically.
In this result is the expectation of this quantity inverse
Yeah.
over distribution of x.
Yeah. Yes, yeah, of course. Yeah, very good. Sorry. Very good catch. Yeah, because this is the X, right? This is what comes out of your random feature step in your data processing. C. Oh la la. My bad. Good catch.
That's an expectation over C.
Yeah. It's an expectation over the inputs. So the inputs of the random features, so C. Yeah. Sorry. Okay.
Can you remind the definition of delta and gamma?
So gamma is just the rich regression factor, right, from my optimization. And okay, for delta gamma, there's a fixed point equation that you need to solve. I can write that down. So delta gamma is the solution of this. My point here was really, so this is really discussed well in obviously these two papers and then also in Alice's lecture notes from last week. So my point here was really just to show how you can also think about this random feature analysis as an analysis of features that come from a random one-layer generator. Okay, and so that's one way of using random matrix theory in this problem. Okay. Okay. So now we want to compute things when the inputs x are still the output of a one-layer generator, but now, we want to look what we can say when these weights are not random anymore. Okay? And the way forward here is sort of to shift gears a little bit. Okay? So before in this linear regression problem, we really thought about the inputs and sort of about replacing the input matrix with another matrix. Okay? Now, what we really want to do here in this regression task is we want to look at quantities like the generalization error, right? So let me just write that quickly out again. So you have your student, you have your teacher, and you're taking the expectation again over the data, so x and c. Now what you'll notice here is that the inputs x and the latent variable c, they don't appear by themselves, like in the linear regression problem. They only appear through these sort of local fields. So they only appear in combination with the teacher or the student weights. Okay? So I can replace my average over the inputs and the latent variables with an average over these lambdas and these nus. Okay? So in other words, if I can say something about the distribution of these lambdas and these nus, I won. And in particular, if these variables have a particularly nice distribution, I might even be able to do these integrals. Okay? And these local fields, they appear a lot. So they appear, for example, in the analysis of the online learning that we're going to do. They appear in the expression for the generalization error. If I want to do batch learning, for example, I want to do replicas, then the replica people among you will recognize these as the local fields that you introduce with your delta functions, and then by rewriting the delta functions in the Fourier representation, you'll also need to do an integral over the distribution of these guys. Okay? So if we really want to understand the distribution of the lambdas and the nus here. Okay? And if you step back a little, sorry, go ahead. Yeah. I mean, I'm assuming in the sense that, okay, if I want to do the integral, I need to know this function, yes. But for the moment, I'm not specifying it. You mean, no, it could be different. So you could train a ReLU, okay, now I get it, sorry. Yeah, you could train a ReLU student on a sigmoidal teacher, or, have a linear regression output and train a really complicated neural network on that. No problem. Okay? Now, what can we say about these guys, lambda and nu? Now, if we go back a little bit to the vanilla teacher-student setup, where the inputs were IID Gaussian, the situation is actually really easy, because if you write out the field, you'll see that this is just a sum over IID random variables, and so by the central limit theorem, these guys are Gaussian. Okay, and similarly for the teacher-student weights. Okay. So if xi are IID Gaussian, then the lambda k's are Gaussian too. And similarly for the local fields. And so that's very nice, because then I can do these integrals because I know how to integrate over Gaussian distributions, right? And the Gaussian distribution of these guys will have mean 0, and then the covariance of these random fields will be the usual order parameters, and I can work with that, and that's basically the way the teacher-student setup is usually analyzed, or has been analyzed. Okay. Now, a model that has this property, we're going to call this the Gaussian equivalence property, okay? So if a model has this Gaussian equivalence property, it means that these local fields are Gaussian, and we can do things. We can, for example, calculate the generalization error, or we can calculate, we can do replicas and so on. So the question is now, does this Gaussian equivalence property also hold if my inputs are coming from this generator? Or more precisely, under what conditions on the weights of the generator and of the weights of the student does this Gaussian equivalence property hold? Okay? And when we started playing with this, what we noticed just numerically first was that even if your inputs come from such a generator, the local fields are still Gaussian. So we could do the analysis. And then we had some physicist-style argument for this. And then Galen Reeves came to Paris and visited us. And he got really interested in this problem. And he found a very nice formulation for this. And he proved it. And so what I want to show you now is Galen's proof of the Gaussian equivalence property for these single layer generators. And you can find that in our paper on the archive. That's 2006. Where did I write this down? Here. Okay? So again, the goal is to prove that these two guys are Gaussian. Now this is really simple to express as a goal, okay? How do we make this, how do we formalize this, this notion of Gaussianity, or almost Gaussianity? We're going to introduce distances between distributions, okay? And in particular, we're going to look at total variation between distributions. What does that mean? That means that, okay, I give you a probability measure P on R, and I give you a second probability measure Q on R. Okay, and I want to know what's the distance between the two. There's loads of things you could measure this, Kullback-Leibler divergence, all these F divergences. Now, if you look at total variation, and we're going to call that D, what you look at is the following quantity. So the idea is you take a test function, F. And this test function could be pretty much anything. You want it to be differentiable, okay? But you have very weak conditions on this. You want it to be differentiable a few times, okay? But then, okay, you take this test function and you compute the average of this test function under the distribution P and under the distribution Q, okay? And you maximize the difference between the two over all the functions in this input space, okay? And you can verify this after the lecture, or you can just believe me, this is a metric. So this has all the nice properties of a metric that we want. So it's a really valid way to compare these two distributions, okay? Yeah, there are some technical conditions on F. Yeah, okay, you need it bounded. Yeah. But now, okay. This is very nice conceptually. Now, I said this was, for probability distributions on R. And here, what we're going to be interested in is multidimensional probability distributions, right? You have one lambda k for each hidden node of the student, and then you have a new m for each hidden node of the teacher. Okay, so we need a way to deal with these multidimensional distributions. And the way to do this is to introduce another measure, which is called the maxed slice distance between distributions, which now live on R to the, k. And the idea is to define this again as a sub over a set of test functions. And, actually, let's write it like this. So basically what we're going to do now is we're going to maximize this distance that we introduced over all the possible vectors with unit norm, okay, such that the projection of the distribution in the direction of alpha and the projection of q in this direction have the maximum distance, okay? So if you will, there's two subs in this definition now. There's one over the function, the test function that you use to evaluate the difference between the expectations, and there's another one over the vector that you use to project this k-dimensional distribution down to one dimension. Okay?
Two distributions that you want to compare is one with SI and SI coming from.
I'll come to that in a second. For now, this is just a distribution between, this is just the distance between distributions. What I want to compare later is the distribution between these two guys, that's a Gaussian distribution, and the distribution of these two guys when my x's are actually coming from this model. Okay?
What's the name of the distribution?
That's the max sliced distance. And it too has some nice desirable properties that it's a distance, you know. Convergence with respect to this implies convergence in terms of MSE and all these things. Okay? I'll let you pause for a second. Yeah. How it's done? You can think about it as just really simply a dot product. Okay, think about, so this is a probability distribution over k variables. So it has, you can think about it as a vector in k dimensions with k entries. Okay?
So is that the Hansel transpose?
It's two vectors, so. But okay, if you want, you can make it an alpha transpose, okay? So you have this k-dimensional vector, right? And here's another k-dimensional vector, which gives you, and each vector gives you the distribution for each variable lambda k, okay? And so now what you're going to do is you're just going to dot this with some vector. It could be, for example, the all ones vector. Then this would be just the sum of all the probabilities, okay? And now you look at the distance of this probability with this measure. And now you're not doing this just for the all ones vector. You're actually taking, you know, the worst vector that you can have. So the vector that maximizes the disagreement between these two distributions, as long as the norm is, you know, bounded. Yeah, I mean, you can think, basically, you can think about it as, you know, so P would, for example, be would be this joint distribution, okay? And so you can represent this as just, you know, three-dimensional vectors. Well,
Is it fair to say that alpha t is the distribution of alpha dot x for x is the distribution of alpha dot x for x from t?
yeah. Is that better? Okay, then take more used explanation. And then that way you get a scalar quantity, right? And then, thanks. Okay. So the two distributions that we want to compare now are the actual distribution of, you know, lambdas and nus when things come from this model. Okay. And we're going to call this distribution p hat. And the second distribution is the distribution that we're going to call P. And that's the same distribution, that's a normal distribution, okay? Multidimensional normal distribution, which has the same mean and the same variance as P hat. Okay? So in other words, what we want to know is, I've got this actual distribution of activations that comes out of my model. I've got a Gaussian distribution that has the first two moments matched with this distribution. What's the distance? What's the distance in terms of this distance that I just introduced? Okay? Yes?
So there is a way, so there is a paper by Resolvent,
Mm-hmm.
actually called random manifold.
Mhm.
They have a distribution that is complicated distribution. It lives in a dimension, and then what they say, okay, let's give this distribution with a Gaussian with same mean and same variance.
Mhm.
They have a free energy that is a variational one, and so they get the equations for mean and variance. And what they show is that when you take the large and limit by just diagrammatic methods, the two things are just equivalent. So for if you want to compute the free energy, you just need the Gaussian. Is this the same speed?
I guess it's the same spirit in the sense that you're trying to find a good Gaussian approximation to a complicated distribution. It's different in one important sense at least, namely that these guys are low dimensional, right? If you remember, so what's thermodynamic in my problem is the input dimension of my neural network. And then the hidden nodes are order 1. So there's 2 in the student, 2 in the teacher. So there's 2 lambdas and 2 nus. So this is a low dimensional distribution. Okay? And I don't think they're intimately related for the simple reason that Mark was involved in this problem. And so it doesn't seem that there's a straightforward application of these methods. And I think that's because, in your problem, I think you're talking about a high dimensional distribution, and here we're talking really about something that's in 4 dimensions.
But actually, there they have a manifold with infinity, and then they have like n variables. So you have 2 dimensions. There is one that is like a dimension that is orthogonal to the manifold, and the other one is the dimension where the manifold is embedded. And you can keep one that is finite and the other one that is divergent. So
Okay.
it's
Okay. I mean, I don't know this particular work, but I guess the person who knows these 2 works the best is Mark, so we should send him an email.
That's what I was just doing.
Yeah, check that. I'm curious now. Okay.
Well, it's just physics. We do silver.
That's, yeah. But we do a very physicsy thing, right? We're just beating the thing so long until it becomes Gaussian. Any other questions? Okay. So yeah, so what I want to compare is again the distribution of these local fields as it actually comes out of this model, and a Gaussian approximation to this distribution, if you will, that is Gaussian and has the same mean and variance as these 2 distributions. Okay. Now I'm going to make the following assumptions, and this is of course where the interesting stuff happens. So the first one is, okay, we're going to have some normalization condition on the weights of my generator. Okay. That's not that important. That's just sort of to fix the scales. Now we're going to make an important assumption on the correlation that these weights can have. Okay? And let me just write it down, and then we can talk about it for a second. That's the technical condition. Now it doesn't really look like it maybe, but what this really is it's a condition on the covariance matrix of your weights, right? Remember, we can collect all the weights of my matrix, of my generator in the matrix, okay? And now we're looking at the covariance AAT, if you will, of this matrix. And now, this matrix, since we've chosen this normalization, will have just, identities on the diagonal, okay? And then, on average, it will have elements which are of order 1 over square root of n on the off-diagonal. Yes.
Just to remind me, A is fixed here, it's not random.
Exactly. So yeah. So really good point. So what we basically the whole thing that we're trying to think about now is another way to say is what kind of conditions can we have on A when it's not random, such that these guys are still Gaussian.
And by AN you mean a column?
Yes, exactly. Of this matrix. Yeah. So this is a column vector that multiplies it with C.
Why is it 1 on the diagonal?
That's just so. I could also put n on the diagonal, and then the off-diagonal elements would be order square root of n. There's sort of a 1 over square root of n difference in between the orders here. Exactly, and since because I chose the scaling to be 1 here, I will have 1 on the diagonal here. Okay? So what's important is that, okay, on average, indeed, these guys will have 1 over square root of n correlation. What's important now is that actually this condition allows for a finite subset of these columns to have correlations which are order 1, 2. Okay? So there are some ones here, if you will. Just so that on average this thing is still 1 over square root of n. And that's important because if you want to handle correlations in your weight matrix, then this is really what allows you to have some strong correlations between some of the weights in your generator. Okay? So this is just, yeah, a technical point.
Constant are sort of relevant in scaling this, but you get one on the diagonal. Why is the diagonal so strong?
Well, because, okay, think about what you're doing here. So think about the random case. Okay? If I drew all my A's randomly, what you would have, and with this normalization, then you would have ones here, and just, some, in the n to the infinity limit, random vectors are exactly orthogonal to each other. Now for any finite n, these guys will be order 1 over square root of n for random weight vectors A. Okay? Why not? If I draw them randomly,
Yes.
they will be orthogonal almost
Yes.
exactly.
So you diagonal at your matrix.
So this is the matrix A transpose, okay? A is the weight matrix of my generator. Right?
This is A transpose to go.
Yeah. I'm trying to understand the covariance condition on these guys, okay? So, you could also choose the normalization here to be n, and then you would have n on the diagonals, and something like square root of n on the off diagonals. So which scaling you choose here is not that important. And I like to have ones on the diagonals, so okay.
No, what I didn't get is that that was A.
Sorry, yeah. What's important though is that there are some correlations between these weight vectors which are order 1. So some of these vectors in my generator, they're really strongly correlated. And this is to model that what happens if you train this generator on some real data. Some of your weight vectors will be strongly correlated. Okay? And so this is something that's covered by this condition. Okay? Then there are some more conditions on the order of things. So we're just going to say that to keep things comparable, we're going to keep the weights of order 1, okay? And then we have some more technical conditions on the activation function of your generator, okay? So we're going to say it's thrice differentiable, that sort of thing. And you can look to the paper for the full details, okay? So that's the setup. And we then have the following theorem. So, okay, let P hat be the distribution of lambda and nu. P be a Gaussian distribution with same mean, variance. Then the max slice distance between P and P hat scales like this. So there are 3 important terms. I'm just going to write them down. And then we're going to go through them one by one. Okay, what did I forget? Okay. So these two, so this is W. These are 2 matrices, M1 and M2. And these 2 matrices, I'm going to write them down in a second. They control the covariance of the inputs that come out of your generator. Okay? So basically what this is saying is that to leading order, the distance between these 2 distributions, it decays. It goes like 1 over square root of n. That's good. Okay? And what we need to control now is how the weights of your student, so that's the weights you're training in your student, how they align with the covariance of your data. Okay? So the covariance of the inputs x that come out, they enter these 2 matrices. And then there's also a condition on the correlation between the weights of your teacher and the weights of your generator. Okay? But morally, what this is telling you is that you're good. The distribution of lambdas and nus is Gaussian in the thermodynamic limit, as long as this product between your weights and the covariance of your data doesn't grow too big. Okay? And now let's spend a couple of minutes to look at what these matrices exactly look like and what this too big really means. Okay? Yeah. So the third term, if you will, are static quantities. That is teacher weights and generator weights, right? So they shouldn't be too aligned either. Because remember, we're not just, so I'm talking a lot about the student local fields, but really this is a distribution over the student local fields and the teacher local fields, right? And so if the weights of your teacher are crazily aligned with the weights of your generator, then that can mess up things too. Okay? But to me, the interesting thing is really, because this is also the thing that's evolving in time, is the role of the interaction between the student weights and the correlation in your data. Okay? So let's have a look at these two matrices. So first, let me define three constants. So I didn't specify exactly which activation function I use in my generator, right? I just said, okay, xn is equal to sigma a and c. Now let's define the constants sigma I and sigma 3. So use just a standard ID, just a standard Gaussian variable, okay? And you can see that these two constants are basically the expectation of the first three series coefficients of the series expansion of the activation function in terms of Hermite polynomials. Okay, so this is interesting because this connects a little bit back to the random matrix theory results, right? I told you that in the random matrix theory result, the activation function sigma of your generator didn't really matter so much in its details. It only mattered through this expectation, of the, as Stefan rightly pointed out, matrix that looked like this, right? And so here we have something very similar in that the activation function only matters as far as these three constants are concerned. Okay. Now, what are these constants good for? Well, they enter the definition of this matrix M. Let me call rho the matrix AAT, okay? And let me call rho tilde the matrix rho without the diagonal. Okay, so this is an n times n matrix, and here I've taken the diagonal out. Then my two matrices, M1 and M2, look like this. Oof. Can you see this at the back when I write it down here? Okay, so these are the two matrices that sort of encode, and they just come out of the proof, okay? But these are the two matrices that basically reflect the covariance structure in the inputs in our theorem, okay? And again, broadly speaking, they are variations of your covariance matrices. The circle here is the element-wise Hadamard product, okay? And that's it, I think, yeah. Now this is a bit cryptic, or at least I find this maybe a bit hard to parse. So maybe what's useful here is to think a little bit, is to think about two examples and what they tell you, okay?
So what's your definition for M1 and M2?
Yeah, so, okay, if you want, this is the definition, but these two matrices, they sort of fall out of the proof.
And all the sigmas and rows have the heads.
All, yeah, they all have the head, sorry. Well, no, not all the rows. So there's a difference between row and row tilde, right? One has the diagonal and the other one doesn't. That's important. All the sigmas have the head, and I've been a bit sloppy with that. Exactly.
Can I ask
Yeah, ask us, you know.
so when you write, for example, the Adama product of rho tilde and rho tilde, that's very tiny because rho tilde has
Yeah.
only 1 over n.
Exactly,
The way you-
exactly. That's the way to think about it. Okay, this looks a bit cryptic, and you know, using a sort of hand-wavy thing about how the data shouldn't align with the data structure too much. Let's try to make this a bit more precise. Okay, and let's look at two examples, which I think make the idea a bit clearer, and which also raise a really interesting open problem. Lenka? Do I have until 15 or 30? 30, nice. You still hanging in there for 25 minutes? Okay, good. First example. Let's take a simple case where the elements of A are all IID Gaussian. Okay, this is basically the random feature case that we looked at with random matrix theory in the very beginning of the class. Okay, what this means is that your first matrix here, and this is easy to verify if you want, is of order 1 over square root of n with high probability over all these random matrices A. So that's good. Okay. And you can see this because if the A's are IID random, then this guy will have 1s on the diagonal, 1 over square root of n everywhere else. There's a 1 over square root of n here. And so, if you write this down, you can convince yourself that this matrix here is going to scale like 1 over square root of n, or its norm. So we're good. Okay. What about the second matrix? The second matrix, M2, it will have one eigenvalue, which is order 1, if sigma 2 is not 0. So for example, if I take the sine function as the activation function, okay? Then there will be one important eigenvalue here for this matrix M2, okay? And this eigenvalue, it's associated with the all ones eigenvector, okay? And so, in other words, and the rest of them will be order 1 over square root of n, so they're not going to annoy us. So in other words, as long as 1 over square root of n of my weight matrix, or of one weight vector, and the all ones vector stay of order 1 over square root of n, I'm good. So in other words, what is correlating your input, your weights with your covariance of your data mean? Here there's one really dominant direction in your data. That's the all ones vector. Okay? There's one dominant direction in this matrix. So as long as your weight vector stays away from this all ones direction, which is very particular, you're going to be fine. But as soon as the weights would align with this direction, then this guy is going to be order 1, and this whole thing is going to blow up. Okay? Now what's interesting is, okay, now you may ask me, okay, does this happen? Okay, now what's interesting is that if you start with your W, for example, small initial weights, but mixed signs, that kind of stuff, IID random, and you run the simulation, the weights will never align with this dominant direction. The weights will always stay away from this direction, as long as you train, even if you train for very long times, even if you train on a lot of data, and it's not really clear why that is the case, right? So the get sort of tells you as long as that is the case, the local fields stay Gaussian, and you can do your analysis, and all is good. And now if you run the simulation, you'll see that indeed this never bothers you. And what's an open problem, if you will, is to understand from a dynamical point of view why, starting from a random initial condition, your weights never go into these dominant directions of the data, right? As you might expect. So it's still an open problem. So this is for the random case. Yeah. I'm saying what?
The top eigenvector of this of the matrix M2 is uniform.
Yeah, it's the all-ones vector.
Why is that true?
It's like it's kind of a Frobenius-Perron kind of thing. The top eigenvalue of this matrix, there's one top eigenvalue of this matrix, and that's, and the associated eigenvector is the all-ones vector. Yeah. Okay. So this is the example for the random weights. Okay. Now, of course, I said the whole point of this is trying to do this with non-random weights. So let's look at another example. And this other example is a deterministic weight matrix. Okay. So let's say that, again, I'm using, for example, the sine function in my generator. So again, all my Hermite coefficients are non-zero. Okay. And as my A transpose matrix, I choose the following form. I choose the identity plus 0 square root of n, the all ones matrix minus the identity for some c bigger than 0. Okay. So this would be an example of a deterministic matrix. Now, M1 for this matrix has one eigenvalue, which is of order square root of n. Okay. And the rest is 1 over square root of n, so the rest is okay. And M2 has one eigenvalue, which is of order 1. And the rest is 1 over n. Okay, so again, there's one eigenvalue in here which is sort of bothering us, because it's very big. And in both cases, again, the leading eigenvector of these guys is proportional to the eigenvector. The leading eigenvector of these guys is proportional to the all ones vector. Okay? So in other words, we have the same condition as we had previously. As long as my weights stay away from this all ones direction. So in other words, for example, as long as my weights have mixed sign. Okay? I'm good. And the get holds. I want to say has one eigenvalue, just one. Yeah, sorry, so this is the top eigenvalue. And the rest of the eigenvalues are order 1 over n. So we did this example when we were writing the paper, and that's what we found. I'd have to remind myself. Again, this was an example just to construct, just so you have this all ones eigendirection, which is really large with the eigenvalue. I need to look back at my notes exactly how you get the scaling. Okay. So to summarize this, what the get is telling you is that, in this formulation, is that you have your data, you have your covariance matrix of that data. It has some dominant eigendirections, the sort of stuff that you would find if you find PCA. And as long as the weights in your student don't align too much with the eigendirections of these large directions in your covariance matrix, you're good, and the local fields lambda and nu will stay Gaussian. Okay. Now maybe a slightly simpler way to think about this, about what we actually did here, is the following. What we're basically saying is that as far as these two-layer networks are concerned, these two-layer networks with this particular shape, where the input dimension is very large and you have order 1 hidden nodes, you can sort of replace your matrix X, which is your training data, with another Gaussian, with another matrix. Okay, let's call that X tilde. And this matrix is basically sigma 1 plus AC plus okay, so you have your real data matrix, and what the get is telling you is you can essentially, for these two-layer networks, replace it with a different matrix that can be written like this, okay? Where the sigmas are again, the Hermite coefficients of my activation function. W is some IID Gaussian noise, drawn element-wise IID from the normal distribution, okay? And here we have the weights of my generator times the coefficients. So importantly, you've sort of changed this nonlinear data matrix, right, which was given by sigma AC, with something that's now linear in your weights and the latent variables, okay? And so these two matrices will have the same first and two moments. And so from the point of view of the two-layer network, they look the same, okay? And what the get sort of gives you is quantitative control over how similar they look to each other, these two matrices, okay? And it gives you some really precise intuition on how you can break this, what can go wrong, right? That's this alignment of the weight vectors with the eigendirections of the covariance matrix. Okay? Yeah. The get involves? Yeah. Mm-hmm. Is this always true? So basically, the rigorous statement is, okay, so the get is about the lambdas and the nus, okay? And you can think about the lambdas and the nus as low-dimensional projections of your high-dimensional input vectors, right? And then the get tells you that the distribution of these low-dimensional projections is almost Gaussian, and it quantifies that, with the statement that we had before. And another way to think about this is that if you can replace your nonlinear data matrix with this matrix, and then if you look at the statistics of the low-dimensional projections of these guys, they are Gaussian, sort of by construction almost, okay? That's a really good point. We want to call that C. That's true. Sorry, yeah, that was confusing. Okay? So another way to think about the fact that these guys are Gaussian is that we can replace our data. I said earlier, if in the vanilla teacher student setup, where the x's are IID Gaussian, the lambda k and the nu m, they are immediately Gaussian simply by the central limit theorem. Because you're summing over these xi's, and the xi's are Gaussian, and so you're good. Okay? And now the gets, with all this machinery, showed you that actually these lambdas and mu stay Gaussian. And so a heuristic way to think about this is that actually your inputs for this two-layer network, they still look roughly Gaussian. Gaussian like this. Okay? That's sort of the essence. And you can also think, this is also a useful way to think about these spectral results of Loire and of Songmei, right? You can sort of replace your data matrix with a matrix that's slightly simpler to analyze. You can say something about its spectrum, and then you can calculate these spectral integrals, which give you training error, test error, and so on. Okay? And we're still exploring ways and thinking about ways where you can sort of do this replacement thing. Okay? Maybe one last important point. So for the get, what's really important conceptually is this bottleneck, that you're projecting down these high-dimensional inputs to something that's low-dimensional. Okay? For the spectral results, the idea is to replace an intractable spectral density with a spectral density that you know, that you can compute. Okay? Morally, they're related to this Gaussian replacement of your data matrix. But at least as far as we know, and we tried a little bit, there's no way really to go from one to the other. So there's no way to say that, okay, I have this deterministic equivalent for my resolvent. Now from that follows that my low-dimensional projections are Gaussian, and vice versa. Okay? They're sort of morally collected here, but at least we didn't find a clear, rigorous way to go from one to the other. So to me, that's sort of two sides of this coin.
So if I've understood correctly, what you're saying is in this low dimension, it doesn't matter if the input is random or it comes from some structure. If you choose these A's like far away from the borderline cases.
I'm not saying that it doesn't matter. What I'm saying is that the only moments of my distribution X that matter are the first two. So as long as I choose Gaussians which have the right first and second moment, and because you're smart, you've centered your data matrix, so we're really talking about matching the covariance here. So really what this is saying is that for these linear regression problems, or for these neural networks with order 1 hidden units, as long as you match the second moment of your data, your network will not notice anything. It will still look Gaussian, yeah. Okay? In other words, if you have something crazy going on in your data at the fourth order, you'll need a more powerful neural network than this two-layer thing in this limit to find it, or to use it. Okay?
If you think it's strong nonlinearity, you have trouble finding the structure in the
A strong nonlinearity in the generator. Strong in the sense of?
In the sense that you're presenting the manifold is some function that is very much more.
Mm-hmm.
Can you see this reflection into the variance in this equivalence?
You can sort of see almost the opposite. You can see that, say for example, I take the sine function as my activation function generator, right? That's pretty violent in terms of, just pushing everything either to plus or minus 1. What this is telling you, and you can see it very neatly here, is that it doesn't really matter so much. It's only the first few coefficients of your activation function that enter this equivalent Gaussian model, okay? So in other words, in this high dimension, the effect of the nonlinearity, it gets washed out a little bit. And so what survives is the first few moments of the expansion of your nonlinearity. But again, if I chose a different activation function that's maybe smooth or whatever, that has the same coefficients here, it will look exactly the same as the sine function. So again, this is one of the things where sort of the high dimensions are slightly non-intuitive, right? If you think about the sine functions in 1D or in 2D, it looks really violent because it really reduces your, it's a really restrictive mapping. But in high dimension, it really conserves quite a lot of this linear transformation. Does that make sense?
Yeah.
Are there any other questions for the moment? Okay, I'll let you think about it one more minute. Antoine, can I go to the beamer now? So I have sort of two outstanding depths to you at the moment. The one is we've talked a lot about these lambdas and these nus, okay, and I've really insisted that it's important to know them. And you saw that if you want to calculate, for example, the generalization error, you need to know the distribution, and if you really want to calculate the generalization error, you need to do some integrals over this distribution, so if it's Gaussian, you won, okay? So that was the motivation for us to look at these fields. Now, what I'm going to show you next time is that these fields are also important if you want to, for example, analyze the dynamics of online learning for such a model. So we're going to train the student with SGD, and we're going to see that if this property is fulfilled, we can actually analyze this in some detail. The way this works is nice. Okay, and so we're going to look at these dynamics the next time. The other thing I told you was that, we didn't just want to have one-layer generative models in our deep manifold model. We wanted to have some more complicated generators, some deep generators, some pretend generators. And so for the last 10 minutes, let's just quickly see how far can we push this on the generator side, okay? We've talked rigorously here about this one-layer generative model, okay? But nothing stops you from checking whether if you put some really complicated model in here, whether these lambdas and mus stay Gaussian or not. Okay. Now, one way to do this is to look at the dynamics. Okay, and this is what we did, and I'm going to show you some examples of this now in these slides. Okay. So what we're going to do now is we're going to replace this one layer generator that we looked at with something that's deeper. Okay, and I've just written this sort of in a conceptual way here. So you still start with a Gaussian vector, but now you propagate it through a deep generative network. For example, one of the networks that we looked at was this convolutional GAN. Okay, so that's really good to generate random images. I'm going to show you some examples. It's a 5-layer neural network, and it has lots of convolutions, and it does a lot of magic, and it gives out an image at the end. The way we're going to test whether this get holds, so the way we're going to test whether these lambdas and the nus hold is the following. We're going to close our eyes and we're going to forget about the complicatedness of the scanner. We're just going to say, let's assume they are Gaussian. Okay? If they are Gaussian, we can analyze what happens if you train the student using this online SGD. And I'm going to show you on Friday how exactly that works. Okay? So let's just say we do this analysis using this assumption. Okay? And what you find is then you introduce some order parameters in the usual statistical physics sense. You find some ODEs for these order parameters and so on. That gives you a prediction for the dynamics. Okay? And we're going to test the get by comparing the prediction that you get from this dynamics to what you see in simulations. Okay? And what I'm going to try to convince you is that if the prediction from these ODEs for which we've used the get agree with what I see in simulations, it's a pretty good indication that something like the get holds even for these deep generators. Okay? It's a conjecture. Again, we're sort of going on thinner ice here. Yeah, we're going to go through the derivation of these equations next week. Okay? Okay, that's actually on Friday. Maybe the only thing I'm going to say here is that what's maybe important or interesting is that the only way you can ask now, okay, what happens if I, change from this simple generator to a deeper generator? What sort of properties of the generator appear in my equations? And it turns out it's only really two quantities. One is the input-input correlations. Okay, so that's what we called rho in the proof, right? And the other thing that appears are the input-latent correlations. So that's the correlation of you start with a vector c, you get a vector x at the end, and now you look at how the two are related statistically for a given GAN. That's the only two things that enter from a generative model. So, for example, what doesn't enter are the weights. Or at least not explicitly. Okay? Now let's have a look at one of these experiments in a case where we actually know it should work. Okay, and that's the case of this single-layer, fully connected generator. What I'm going to show you always the same kinds of plots. Okay, if you want to, you can really only focus on the top left plot. What I'm plotting here is, as a function of training time, the test error of the student. Okay. So I'm training the student in this deep hidden manifold model. I have a test error. And the lines are what I get from the simulation. So I just create a test set, and I evaluate the student on this test set numerically. That's my simulation. On the crosses are basically the prediction for the test error that I get from my dynamical analysis. The dynamical analysis that was based on the get. In this case, we know that the get is true, right? We have Gaussian's proof, and it's very neat. And indeed, as you can see, for the test error, the two things agree very well. And they don't just agree for the test error. Here are sort of the dynamics for the order parameters. We'll talk about that on Friday. But you can see that the agreement is pretty well for all of them. That was expected. Yes?
What is your n?
My n is, is 8,000. And my latent dimension is 800. Okay?
How do you know because for this model you know.
How do I know what?
No.
Yeah, for this model I have the proof that the get holds. Okay? So this is what we can expect from a model where the get holds. Now let's do the same game, but with the deeper generators, okay? Yeah, one nice thing is you can use the ODEs to then predict stuff. We'll talk about that on Friday. Okay, now let's use this deep GAN, this 5-layer GAN. Here's just to give you an idea. This is what the images look like that come out of this GAN if you trained it on Cypher 10. Okay? And the point here is just that these are the sampled inputs X, and clearly there's some very non-trivial correlations going in, right? This really doesn't look like IID Gaussian inputs. This doesn't even look like some Gaussian approximation to something, okay? These inputs are really fairly structured. Now, if I give the GAN random weights, what I'm basically checking is what happens if I sort of have spatial correlations in my outputs, right? Because my network now has these multiple layers of convolutions, so there's some spatial correlations that get introduced here even by these random weights. And you can see that the agreement is still pretty good. So for this random generator, random in the sense that it has random weights, the get still seems to hold. Now what about the generator that I used to generate these images? Okay? And here you can see that that's this experiment. You can see that for the test error, and for example, these are the second layer weights of the student, the predictions are still pretty accurate. But, okay, I'm not going to lie, for some of the order parameters here, things break down a little bit after, say 100 steps or something. And so we looked at this and we thought about it a little bit. And one thing we noticed is that the input dimension for this GAN is very small. Okay, it's just 100. And so we're comparing here in thermodynamic theory, where n goes to infinity, to a case where one of these dimensions, the problem is actually quite small. So there could be some finite size effects. Okay, there could also be some correlations that we just didn't properly account for. We checked whether this is maybe just a finite size effect by going to another kind of generative model, and that's going to be my last experiment. This is 100 because you really start with a 100-dimensional vector, and then the network sort of turns that vector into a square image. 3072. So one of these dimensions is large, but the second dimension, this d, is small. It's just 100, and we actually in the theory we have both of these go to infinity at the same rate. Okay, so one source of the error here could be just some finite size fluctuations.
Your theory for d going to infinity.
Yes. Yes. Yeah. And so there's actually a very nice kind of generative model which sort of gets rid of this small d problem, and these are normalizing flows. Max mentioned them last week. What's nice about them is that they are basically a generative model that takes, again, a vector and transforms it into an image, only that it's a reversible transformation. So in other words, the input dimension of your generator and the output dimension are the same. So both of them are pretty large. Okay? And one example of these normalizing flows is this real NVP model that came out from a few years ago from Google. Okay, here's again an example of Cypher 10 images and the images that are generated from this normalizing flow when it's trained on Cypher 10. Okay, so again, these inputs are fairly structured. And this is the comparison of the theory to the experiments. Okay, and now you can see that not only the test error but also the order parameters agree really well with the predictions from the ODEs. Okay, and so if you believe me, and again, the big thing that's changed here is that the input dimension is now also very large. So, this is pretty strong, I think, experimental evidence that something like the GET even holds for deeper generators, right? That the local fields here are also Gaussian. Proving this is a different business, and that's still something that we're working on at the moment. If you want to, we can chat about this in the coffee break. But some of the techniques that we used to prove the GET here, they don't readily apply to the deep case, but we're on it. Okay. So I'm confident or hopeful that it's going to work. Okay, that's it for today. Thank you very much. Tomorrow we'll talk more about how to use the GET to analyze the dynamics of the networks. And yeah, thank you very much.